All right, so let's do this. A couple of months ago, when Felipe reached out to me and asked me to do this presentation, I didn't realize two different things. The first one was that I'm going to miss Adobe Max for this one, so Felipe, that's on you. And the second one was that I would be super excited to be in a whole new country and see like the whole environment here and what's happening to you guys. Today I'm going to talk to you about what we are doing at Adobe to architect the future of web development. As a company, we've been great at doing desktop development for years. We are known for creating overpriced products for everybody that's a professional. So now we're trying to fix that and come back to the new generation of apps which are going to be on the web. Before I start every single one of my speeches for the past 10 years or so, I'm trying to get people to know what exactly I'm going to talk to them about. Just so you know, if you're interested, you can stay. If not, feel free to leave. I will not mind, I promise you. So, here are the chapters of the presentation so far. I'm going to give you some context on me and why exactly am I on this stage and I'm speaking to you guys. Then we're going to go to what are we building or what were we building. When we initially designed this presentation, we were building a product, but it shifted like 3 or 4 times since then. And I'm going to give you some glimpses into what's happening there. Then we're going to talk a bit about the tech stack. For those of you that work in the industry, you might find some interesting data in there and might go home with some interesting information. Some flashback on how challenging this did this look at the beginning of the whole project. A critical path for the app. This is going to be starting to look like really developerish, so I hope you're comfortable with that. A rewind, so that we can have like a big picture of the architecture and how all of that looks. And last but not least, a bit of a deep dive into multiplayer and how does that work. But before we get started and everything, I would really like to just get to know you a little bit better. So can you put your hands up, everybody that's working on the web and has web experience at least a few years? All right, I hit the right crowd. Awesome. All right, moving on. Some context on me. I'm Aleodor Tabarcea, also known as Ale by everybody. I'm an engineering manager at Adobe. I've been building Adobe products for Adobe for the past 5 years or so. And one thing that I like to count is the numbers of users that I usually hit. The first product that I built at Adobe, which was account.adobe.com, is basically still used to this day by approximately 20 million users every single day. Now, as I moved on, like in 2 or 3 years of career, I decided like, hey, building like web applications can be more complex and more enjoyable. So I migrated from the identity part of the company towards the creative cloud of the company. The creative cloud of the company is what you might all know as Photoshop, Illustrator, and all of those products that fall on the devices of creatives. Why am I presenting this and not anybody else? Well, basically, I was the lucky guy that was there from the beginning of it all. I was the first developer that created the MVP or POC for the web applications at Adobe. And I started gathering more and more people around me and create a movement into how we could build these and scale for the future of tomorrow or the next 10 years. A couple of the companies I've worked for, I don't know if that's important or not, but I've worked with Microsoft, I worked with Bitdefender, and now I'm at Adobe, and hopefully in the future, something even more challenging. Moving on. So what were we building at the time? Please keep in mind that this whole process of creating the new architecture for web apps was totally developer-driven. Like there were a couple of developers in one room that decided at some point that, hey, we're going to have to move all of these desktop products towards the web and also cloud services and everything else. So let's do something fun while we do it. And we decided to create what is little known as the creative canvas. What basically aimed to be an infinite canvas where you could drop any kind of resource, be it a Microsoft Word file, be it a Photoshop file, an Illustrator file, or a simple image. You could just drop them in there, and you would get contextual tools in order to be able to edit them and process them in any way that you wanted. Now, as we built this, one of the main key areas that we want to focus on was multiplayer. We wanted to be able for everybody to work on the same project at the same time. And you're going to notice like a common theme across the presentation that multiplayer is pretty hard to do. And we're going to get into the details of why exactly that happens. Looks challenging, right? Well, when I first started to build this system or this product, I've been building web applications for the past, again, 10 years or so, but I haven't even figured out why you would ever need 60 frames per second in a browser, right? Because nobody really needs them. Well, surprise. As we started building this, we figured out that developers and designers are really picky. And all of those gamers that later on transition to be great developers or designers actually want their things to move super smooth on the web as well. So with all of the knowledge that I think I had on the web, on building web platforms, I started to figure out that, okay, this doesn't really scale, and I cannot use it and translate it into building an editor that would be live and all of the people could work at the same time on the same product. A couple of problems at first sight. We got in the room, as I was saying, stood there for like 2 to 3 weeks, with breaks, of course. We went back to our families from time to time. And we started to figure out that there are a couple of problems that we want to tackle. The first one would be the main thread cannot keep up with the number of updates. Basically, as we started to look into files that had like 10,000 rectangles, let's say, on them or something like that, as we moved them around, we would get like a really laggy feeling on all of the interaction that we're doing with them. And why was this happening? Basically, all of the JavaScript running behind the thread and munching at the resources, figuring out what's the new position of my rectangles, the color and border and so on, was just too much for the main thread. And we decided, okay, we're gonna need to split this work in multiple versions of it. Just an English check. Is everybody comfortable with the speed that I'm talking? Can you raise your hand if you're comfortable with it? Awesome, thank you. All right, so the main thread couldn't keep up with us. We decided to do worker threads. Worker threads are basically the superpower of the web browsers right now. It allows you to access into more of the resources of the browser behind the scenes. And we're gonna get into that very often, very easy. The second one is multiplayer games are a pain in the ass. And I'm not joking. Whenever you bring multiple players onto one product, be it a game, be it an editor, be it anything that you want, as soon as those players are going to start crashing to each other, you will not know how to figure out who's right and who's wrong, basically, in that whole equation. The third one was patterns for scale. The plan was, okay, you're 30 developers right now that are going to be building this POC and MVP, and we have like 350 other developers that are going to join you as soon as you have something viable. And we were like, if 300 developers are going to join us, we have no idea how this whole thing is going to scale up. So we figured, as long as we have something well put in place, like documentation and automatic checks across the line, we could make sure that we can scale as much as possible on this direction. The fourth one is bundle size. Well, we figured out that bundle is really hard to keep low. You wouldn't really mind in a web application that you would have like maybe half a megabyte of data to transfer. But as we're starting to build this project, we actually got to 400 megabytes. And 400 megabytes for anybody not having like the speed of light internet is going to be taking quite a bit of time in order for you to get to interact with the application. And working with the latest technologies is great until it's not so great. We were basically saying, okay, we're just going to be doing the latest 2 versions of Edge, Chrome, Safari, and Firefox. These 2 go bundled together because they have a Chromium engine behind them. And we were working with like the latest and greatest in the browsers. And it was so freaking cool. And at the same time, so frustrating. Why? Because the Chrome team usually takes 2 to 3 weeks to answer any question. And the Safari ones, I still asked the question 1 year ago, and I got no answer to it. All right, so this is going to be like the challenging part. We tried to start thinking about the product and how we're going to do. First, we tried to establish the target population. We are trying to move Adobe, as I was saying, from professionals that need super big hardware, super performant hardware, towards the masses, and so everybody could use it. So we decided, okay, we're going to be building these products for a base Chromium notebook for $500 and a 500 kilobytes per second connection. They have to work for this, or we failed in the process. The second one was we had to finally accept there are no more device boundaries. All of that fun part where you defined 3 different design systems, one for phone, one for tablet, and one for desktop, well, it's kind of gone. We now have the Samsung Flip, the Samsung Z, the possibility to extend your desktop from your phone in an instance. So we can no longer think about boundaries as we thought them before. We don't have mobile and tablet and desktop. We just have this fluid ecosystem that you have to go through, and you have to be able to scale up to 8K if needed, or you have to scale down to 720 pixels if needed. And last but not least, as we do usually as developers, we had to drop a proof of concept and see if all of this could work together. Getting to the more techie part now. Okay, what's the tech stack? We started with what we knew in the team and also what we had like battle tested before in the past. We started with React on the front end, TypeScript for all of the business logic that we had, mostly because a lot of our developers were coming from a desktop background and they knew .NET, they knew Java, and they wanted that strong type comfort that came with them. And on the really heavy lifting, we had to pick between C++ and Rust. And one and a half year ago, when we were starting to build this project, Rust was really heavy payloaded. It still is today, but it got a little bit better. But the difference between a C++ text engine, for example, and a C++ Rust engine was the order of 40 megabytes minimized versus 120 megabytes minimized. So we decided, okay, we would be a lot more comfortable with Rust, but we have to think a little bit of our clients and just make sure that we get that small bundle in there with C++. All right. The one thing that we didn't have and we didn't know how to tackle it was state management. And how are we going to do state management? So we had React, we had TypeScript, we had C++, and then we decided, okay, let's do 3 different applications, re-implementations of each of them to figure out what state machine would work greatest for us. We took up like the forums and everything and tried to figure out like NPM trends in order to see what are the most popular ones. The reason behind it is as the technology is more popular, you get more and more supporters that are going to be fixing and repairing things into the app. And also, we kind of figure out like these are the simplest for anybody to use. At the time, MobX was emerging, so to say. Redux was in Crave, just like it's right now. And Xstate was a really cool kid on the block that brought in some new machine organizing stages. So 3 different apps with 10,000 different nodes behind the scenes in order to compute some real information. Basically what we had, it was 10,000 rectangles drawn on a canvas, and you start moving those rectangles. And what happens? Well, first, it was the first contentful page. How much time does it pass since I hit enter on my URL until I get anything on my page and I can understand something from it? And you can see that MobX was winning by far here. The reason behind it, if for those of you that are not familiar with MobX, it uses a proxy system basically that just wraps simple JavaScript objects in order to get the best performance out of interacting with those objects later on. Redux was doing not so bad itself, and also Xstate was there with us. Time to interactive was also a pretty good metric for us to understand like how much time would it take our user to interact with 10,000 objects. These 10,000 objects gotten from a median of how many objects do our users have across Photoshop files or across AI files or across any of the ecosystem files. So in medium, across the 12 or 14 million users that we have, you can find Photoshop files that are around 10,000 objects long. So we figured if we make it work for 10,000, it's probably going to be good enough for everybody. And now this is an interesting one because not a lot of people actually have to deal with it. But whenever you start doing worker threads and you start offloading some of your business logic to a different worker, you have this passing on of the knowledge from the main thread to the worker thread. So on the main thread, you got to do some magic in order to give it to the user and show it something to the user. But as you pass the information over, you actually have to serialize every single object that goes from the main thread to the worker thread. And the same, you have to do it when you come back from there. And that's an expensive overall mechanism that you need to apply. So we try to figure out like, okay, what happens if we use any of these 3 state machines and we start like pushing a lot of notifications or a lot of information from one thread to the other? The really nice surprise here was that Mobix was rocking it again. Since the proxy system did not need any overhead in order to process data as we were deriving information from the existing nodes, it was really fast at applying any kind of update on the UI. Now, the difference between apparent and actual here is a mechanism that we call optimistic updates, and you might be familiar with it. But basically, every single time a user did something, we presumed that the user was successful in doing it. And until we went back to the worker thread, crunched all the numbers and all of the changes, and came back to confirm that, we could actually give the user an experience in 1.8 milliseconds compared to the 187 milliseconds that you would get as you get back from the worker. Moving on, another really nice surprise on Mobix was the memory footprint. Since proxies don't really need any overhead on callbacks or functions in order to process all of that information, and it's just a simple pipeline towards your information that you have, on the same thread, Mobix was rocking it with objects, like keeping 10,000 objects in just 23 megabytes was a really, really nice deal. As we grew bigger and bigger, the objects got more complex. So you can imagine now that having a Photoshop file opened on the web, it could take you almost 2 gigabytes of memory of just knowing what the metadata of the objects in that Photoshop file is and how to handle it. So again, Redux was doing great on all of the above, but when we came down to state management, like actually seeing how much memory does it take, it was actually taking 3 times more than any Mobix counterpart. Now, I could talk a lot about complexity and how do those solutions look, but if you're interested in that, do find me in the networking area afterwards, and we can expand on the topic. All right, we figured out so far Mobix, TypeScript, C++, but there was a little bit of a problem. Our bundle was still pretty big. Like, we didn't manage to hit under 300 kilobytes for the bundle in order for the user to get like a really instant experience of the platform. So we tried to identify the culprit. And the first culprit that came to mind was React. As we were building like a really simple application, we figured out that React was taking more and more of the space that from the bundle. It was actually taking up 138 kilobytes just to show those 10,000 nodes in a list on the right of the screen. And that was all we were doing at that point. We had to build like way more complex UI on top of it, so we were not really comfortable with this kind of bundle size for just this kind of information. You can also see here the build time, interactive, first content paint, and the memory footprint overall. So we started bringing in 2 more competitors. Again, we did 3 different applications, POC each one of them, and did measurements across 5 different instances to make a median of what they were taking. Preact was in vogue at the time. Like, everybody was looking at Preact as an easier version of React with a lighter thing, and also the virtual DOM gone from the system, and it should have taken a lot less space. And it was doing pretty decent, but of course, as a new kid on the block, Preact had a lot of bugs. And after fixing bugs in their library for around 2 months, we decided it just needs way too much energy from our side in order to keep this up and running. So that's how we ended with Lit Element, which is not a framework per se, but it's a library that helps you build web components and easily share them across every other ecosystem that you might have. Web components were not doing great only on bundle size, but they were doing really great on the memory footprint as well. And as I was saying, we were building more and more of those objects, and the complications of the metadata that could come from an object was really large. So we tried to figure out, like, okay, we're not going to take too much of the browser's memory, because otherwise you would get just that little dino on Chrome saying, hey, oops, something went wrong. Behind the scenes, you ran out of memory on that page, and that's probably the problem you faced. So we decided on the tech stack: Mobix, TypeScript, C++, Lit Element. If afterwards you have any questions around any of this, do reach out to me on the networking area, or you can ask questions on Event-T, I think it's called the app. All right, we'll go through the critical path of the app. What's the critical path of the app? I like to call this the redlining of the application. How does the app go from state 1 to state B, and what's the information flowing in through all of this? This is an architectural overview, very high level, so we're going to go pretty fast through it. The first thing that you're going to start off, it's the index HTML, didn't care to put in here. You then have your index TS, which brings everything from the bundle slowly. But we identified we needed a previous step. If you remember the metrics on the other slide, they don't really matter that much, just the decision afterwards. But basically, React, lit element, and Preact were all having the same issue. It took us 300 milliseconds since hitting enter and until the user saw anything on the page. And for us, that was unacceptable. If you had like a really low bandwidth, like having like 20 or 30 kilobytes per second speed, that might have been even more. So you would have ended up having 1 second or 1.5 seconds of a blank screen with no kind of feedback that you're actually reaching our application. So we designed a new kind of subsystem for our application, which is called preloaders. Preloaders, what basically they do, we identified the minimal part of the application that we need to load in order to show a loader and a string that's actually translated in the user's language. And we bring them into these preloaders to offer the user a first experience under 100 milliseconds. Moving from that, we're moving to the main bundle, which is the bundle that brings in all of the other goodies in the system. And we're using a dependency container, which is basically a map from a string to an object that helps us identify all of the subsystems that we want to use into our ecosystem, such as internationalization, error management, or the app stores that keep the information around those nodes. And that's how we build our single-page app. And it would have been really nice if it stopped there, right? Because I already did that. It was awesome. But it didn't stop there. Because we had this other beast on the worker thread, which was actually doing all of the business logic for us. Like, how do two different rectangles collide? What happens when you put an XD file over a Photoshop file or the other way around? What happens if you double-click on a Photoshop file and you want to enter into the context of that Photoshop file? So in comes the second bundle, which is basically recreating the whole application that you have on the main thread on the secondary thread. A similar index TS brings in the main bundle, and then it brings in the business logic or the model of the business logic that you want to have. Nodes are actually a representation of those rectangles, circles, images, or whatever you have on the canvas. Models are information that you want to transfer about those objects, so metadata about the objects. And notifications are basically just nodes coming in from the ecosystem that need to be forwarded toward you. And all of this pipes into those app stores that then pipe into the single app. And still, it would have been really fun if it stopped there. But it didn't. We still needed another piece in the ecosystem, and that's the performance piece. As we were saying, we're building C++ engines in order to touch the really hardcore parts of our application. And some of the hardcore parts that I want to highlight here are the C++ text engine, the rendering engine, or the path engine. All of these have so many variables and so many data to process that you cannot do it in JavaScript and still leave the browser unlocked, even on a separate worker thread. So as we identify each and every one of these pieces in the ecosystem that need higher data processing, we're moving them towards the C++ engine. And Adam afterwards is going to talk about Melee and AI into IntelliJ. One of the modules that we actually have into the ecosystem is an ML module that actually feeds in the information that it gets from the services in order to upgrade and keep up those nodes into different states of prediction based on ML algorithms. All right, this is the critical path for our application. And I'm going to try to rewind a little bit and show you the whole picture, but simplified. On the first layer, on the main UI thread, like whatever you're getting when you right-click and hit Inspect Element, you're getting this information that's user-oriented. It's anything that user can interact with. And on that part, we have the lit element, the mobx, and the TypeScript. All of these working together in order to be able to receive input from the user and give back that result to the user. On the second worker, we have the authoring worker. It's doing some of the heavy lifting of business models, but it just keeps working between TypeScript, which is like the main business logic interaction that you're having, and C++, which is like a secondary systems pumping in data into that business model. This is the second worker that takes care of processing all of this data and hopefully not getting stuck as you process more and more data. And the last layer that we needed, and we decided we had to do a separate worker for it as well, was the rendering worker. As all of these models and objects were changing real time, and we could have, hopefully, we hoped at that point, 100 different people all interacting on the same objects at the same time, you are getting a flood of information from the server and from your local machine on how to update basically your canvas, your UI. So we decided, okay, this can no longer keep up. Like the business logic and the rendering logic cannot live together because it's just taking too much resources and is getting jumped. So we split separately the render worker, which is just going to take care of looking at the scene, figuring out what the object is, and how you paint them on the screen. All right. Now, since I give you like the simplified worker version and how this splits up, I was thinking like I should give you like a more of an overview of how the data gets processed and how everything works in the ecosystem. The first we were talking about was the main browser thread, right? Where we render the UI components that are built with lit. And then as you can see here, we're moving from the UI components to events, which is like pretty classic for all of the UI builders out there. You get the event handlers on the app model, which are basically understanding like what the user is trying to do at that point. And it communicates them forward to the UI state, which has automatic bindings with MobX on the UI. Moving on, we have the authoring worker, as I was saying. At the core of the authoring model is the document model. Like, the document model is an over-glorified JSON file, basically. It has all of the information you need to know about the objects in your file. Like how many images do I have, how many text objects do I have, rectangles, and so on. These all sit as a permanent storage into the document model. Around the document model, we have two different pipelines. One pipeline that picks up information from it, and true view and decoration models, which are a secondary layer of view models, pipes it up into the UI backwards. And on the other side, you get all of the edit operations that come from the app model and feed into this document model in order to update information on the document model. Whenever any operation is not fast enough, or we're seeing that it's not fast enough, we're passing that burden, so to say, to the C++ modules that are processing it and then applying it on the current document model. This is how the schema looks like, and I've introduced like a new topic of information here, which is called the UI sync. The UI sync, think of it like a mediator. It makes sure that the UI part of the application knows how to interpret the information from the authoring application, and the authoring application understands how to interact with the UI. All right, you're going to notice right here the collaboration model. The collaboration model was one of the critical pieces that we built for this app. And it was that piece of information that I was telling you initially that multiplayer is really hard. Well, all of the data flowing into this collaboration model had to go through all of the users that were looking at the document at that point. So it was really hard to create that, and we're going to talk about the delta management system, which is basically sending changes across the line in a few more slides. I'm good on time. All right. The third one, as I was telling you, is rendering. Rendering basically understands how the authoring model looks and what are all of these view models and decoration models, and you pass in the knowledge of, okay, how do I want to paint this information to the user? Because behind the scenes, you just have a JSON, right? But that JSON needs to be translated in something the user understands. More than that, over that JSON, you need to add handlers. Handlers, which is like, I don't know, whenever you get that little arrow where you can rotate an object, that's a decoration model. That decoration model does not exist on the document itself, but it exists in a non-persistent storage or a non-persistent instance of the running of the application, right? And all of these needs to be pipelined into what we call the scene graph. The scene graph is a definition of what the scenery look like. For those of you familiar with Unity, it's basically the environment that you're building all of the objects in, right? Behind the scenes, even more than that, in order to manage all of this document model, we are actually using a ECS system, an entity component system, which creates entities across the line and knows how to interact with each other. Similar to Unity, again, and to other game engines. If you want to know more about it, we can talk afterwards on the networking area. And last but not least, there were external services. From saving the document to cloud, from passing the information through sockets, from all of this collaboration information here, and just making sure that everything that happens outside the app comes eventually inside and propagates through this whole ecosystem. Now, how many of you think this schema is hard to understand? Good. I was counting on that. All right. I tried to simplify it a little bit more for like day-to-day usage and, so to say, like regular application usage. And I built it like this. We have an ECS database, which is like really simple, just a bunch of JSONs bundled together, which know how the objects look like and how to store the information on each of those objects. From this database, you have two things. You have generators, which are basically looking at the data and translating it for other users to consume it. And you have handlers, which receive actions from anybody really on this planet and just know how to apply those actions onto my database. It's a simple transactional system. Over this, we have the UI sync. The UI sync is, again, just making sure that one part knows what the other is talking about and they have a common language. From the UI sync, we get to the part of the UI. And for those of you building web applications, this might be a lot more familiar. What we have here basically is a connector, which the connector knows how you provide information. It can be an API, it can be a socket connection, it can be just the local host that you're reading from. So connectors are basically translating how I interact with the data source that I'm provided with. From the connectors, we move on to the stores, which just store that information in one form or another. And then we have this whole ecosystem of the UI, which is basically what you usually get when you build applications with React, Vue.js, or any other framework like that. The split here is made so that we can reuse easily across different ecosystems. The store manages the information that's not component related, and then we have the component state that manages the information for the component. The smart components are just there to know how to pass data to the render components and how to get events from the render components and apply further on in the ecosystem. Now, you might ask, why should it be so freaking complicated? And the reason why this is so complicated, so to say, is that we want to modularize it in such a way that as technology evolves over the span of the next 10 years, you would be able to swap in and swap out any piece of this whole ecosystem. And the first piece that we did swap out was, as I was telling you, initially we started building everything with React, and at some point we realized that lit element was way more performant. So what we needed to do is basically just remove this little piece in the whole ecosystem. We throw it to the garbage, 20% of our work done down the dumpster, and then replace it with the lit element version implementation for this. Now, across the ecosystem, just making sure that those components that should be aware of external services are aware of, they just need a dependency container. If you remember, the dependency container is just a map pointing from strings to any kind of objects. But behind the scenes, what this gives us the flexion to do is basically swap out any of those containers as long as we keep the same API to interact with them. Again, if you want to deep dive with me into any of this, I'll be outside on the networking area to talk more about it. A bit of a deep dive into the multiplayer, and damn, I'm right on time. All right, so how many of you so far gotten some useful information out of the presentation? All right, I hit somewhat of a bullet mark over there. But then again, I said, okay, I'm going to give them like a high-level overview of what the architecture looks like and how this whole ecosystem builds. It's been battle-proven for the past 2.5 years or so. We're currently building 13 different applications on top of it, and it's turning out to scale pretty well. Different pieces of it have been swapped in and swapped out in order to be better at whatever the application was doing. And just to give you a quick example of how does that work, Recently, we've tried moving, this is like confidential information, you're not going to tell anybody. But recently, we started moving Fresco towards the web. Fresco is our painting app, which basically knows how to understand colors and acrylic colors and how they blend with each other and use ML and AI in order to be able to create those results. So we moved Fresco towards the web, and we figured, well, you know, you don't need a C++ text engine, you don't need a path engine because you don't really have any paths in there. So we were able to easily swap out those modules and create what we called vertical slices of the application that we could reuse from one ecosystem to the other without having to do any overhead. So they get all of that collaboration state, all of that collaboration model, they get it for free on Fresco, and they just add to the system whatever they need in terms of data processing themselves. But I promised you a nice exercise, so I'm going to do a little bit of a deep dive into multiplayer, or the Delta management system. Freaking multiplayer, man. When we first started to build this application, again, we wanted to have multiple users interacting at the same time, give them a collaborative environment to interact with our documents. So the problem we hit on was, okay, user one changes this helmet color to red, and the other guy changes it to green. Who's winning? Like, who's right in this ecosystem? And at the same time, if that was not complicated enough, because you have like a persistent change on the object, in comes the second scenario, where user one and user two both want to drag an object. So you start dragging an image on the screen, the other users also start dragging a user on screen, and again, who's right, and where does it happen? At first, we just said, we're just going to pump everything towards the server. Like, whoever gets there first, it's right. We don't really care about it. But the problem that we saw is, one, there was a whole shitload of events that we had to process, and we didn't know how, when, and in order to get them from the UI thread to the worker thread, it was actually costing us time in order to do so. And the second, you were actually getting all of these kind of objects jumped around the canvas. Because I was right for half a second, but afterwards, the other user got a better connection to internet, and he was more right than I was. So my object was jumping out of my mouse, and I was like, what the hell is happening there? So we went like, okay, we need to fix this. How do we fix this? And I'm going to walk you through two different solutions that we found. One for persistent objects, or for changes that happen on objects and are going to be remaining there, like they're going to be on the document. And some for unpersistent object, like what happens when the user drags something or the user interacts in general with the page. For persistent changes, what basically happens is, as user one and user two both open the project, and they both do a change at the same time. Here, we found it safe to just leave the system or the ecosystem define who's right. So the Delta server that was waiting for these changes, and they got them through a socket connection, got the change one first from the first user, and we were like, okay, we got in change one. Here, you have the confirmation. You're all good to go. But then, okay, what do we do on the other user? At first, what we were doing is we're applying over the change two that the user done. But that created unpredicting behavior. Because you can't really know when you have a complex object, how does the mutation go? So if you go like exactly through the same steps, you're going to get the same result. But if you mix up those steps, you might not get the same result on the application of the user. So what we ended up doing is basically, if the user won on the server, it means it also won on the other user's machine. So we were doing a reverse on the change two. We were saying, okay, you changed the color to green. That's great. We're going to change it back for you on the initial color. We're going to apply change number one here on your object. And then we're going to reapply change two, which is your local change. Behind the scenes, this was happening for the user without him even noticing. Why? Because we were processing it in one frame, in 16 milliseconds for the user. So he was not able to see the fact that the color was going back to green and back to red, so to say. We were just pipelining that in in 16 milliseconds, which is one frame for the user. And then if there was some delta there, like the change two might have not looked like the initial change tool, right? Let's say I applied something on a range, and then if the user one changes the first piece of the range, and I change the whole piece of the range, then I might not be right anymore. The first piece was not in the state that I changed it in. So the first piece, I'm leaving it alone. The second piece, I'm overwriting it with my changes that I reapplied here. I identify what the delta is between the changes that should have happened when the user first made the change number 2. I identify the delta and communicate that delta to the server. The user 1 now has to apply the change 2 delta since I won on the server. And as soon as user 1 changes that, I also get the change confirmation that I need so I can continue my work. How did that explanation work out? How many of you did you follow the whole thing? Awesome. Thank you. Now, we also have the secondary system that I was talking about, which basically means the user does something crazy. And by something crazy, he's not crazy. He's just like starting to play around with our app. And one of the most common use cases that we've seen is basically a user just picking up the color picker and going like disco ball. He was just rolling over the color picker in order to see how nice it would be for the color to change continuously on its object. But all of this was giving us a lot of stress on the systems. You had to process every single change of that color and also send it over to the other guys so they know what they're doing. But at the same time, some other guy might also be playing ball with the color picker. So who the hell was right in this whole ecosystem? So we tried to figure out like, how do we do this? And we ended up with this solution that I'm going to present you. I'm not saying it's the best solution possible. Something better, we might come along later on. But for now, it kind of seems to work. So I'm going to take the instance of a dragging object because it's a little bit easier than the color picker. The color picker goes from UI to authoring, and then it goes on to rendering and so on. It's a whole ecosystem there. But for just dragging an object, imagine like I have a unicorn on the canvas, and I want to see the unicorn flying on the canvas, right? So I start moving the unicorn on the canvas. This child number 1, or adult number 1, because I like unicorns, starts dragging the unicorn on the canvas, and user number 2 also starts dragging the unicorn. It's the same object, basically. And they should be seeing the updates from the other side. But we introduced this, what we called ephemeral forward changes, which is basically we're telling the other guys, okay, I've started moving this object, but I'm still playing with it. You know, I'm not yet convinced what I want to get out of it. So I'm just forwarding this ephemeral changes, and if the object is the same, I'm basically creating a stack. The stack says so. User B is dragging, but since you are also dragging, you are more right than user B in the process of dragging. So you're seeing the result of your own drag on the screen, not the drag that goes behind the scenes as a phantom drag from the user B. These ephemeral changes go both ways, of course. You go from user B to user A and from user A to user B. But in case of user B, user A is the first one that's a phantom user in there and it's just moving things in the background, and I am the guy that's right in this whole ecosystem. As things move along, again, user B continues to drag. I get this drag number 2 here, but I'm still dragging the object, so I'm still more right than the user number 2. And if the clicker works, as soon as user A releases the mouse though, this whole thing changes. Because now I know that the user decided on something. It decided that the unicorn should be on the top right corner of my canvas. What does that mean? That means I have to apply the position to that object to the document model. So I'm sending, hey, now I'm sending a real change to the system. So I want you to apply the new position for the unicorn. And you apply this new position for the unicorn, and on my stack, I noticed that I add another action which is basically saying, hey, I applied this, but the server hasn't yet confirmed that I applied it. So I might change it in the meantime, and if I would be to move fast enough, like under 100 milliseconds, which it takes to go to the server and back, I could come back and still be the correct guy in the stack. As this is happening, Basically, when the server confirms, you apply user A change, and now user B starts to be right. Because you released the object, right? So you're no longer playing with the object. It's no longer locked down for you. So now, as user B is playing with the unicorn, you're actually noticing the unicorn moving from the top right corner into the new position that user B is interacting with it. Because user B is now right in this whole ecosystem. On the other side, as soon as you apply user A, behind the scenes, and again, in the span of one single frame, we're applying the changes that user A done, and then on top of them, we're applying the changes that user B has done on the unicorn, right? So for one frame, basically, behind the scenes, what the unicorn is going to do, if I was playing with it on the top bottom of the corner, it would jump to the right corner where the user A applied the changes, and then as fast as 1 frame per second, it would have moved back to where I was playing with it initially. All right. Similar, when user B releases the mouse, we send a notification to apply user B position towards the Delta system. And at the same time, we add into the stack the apply user B unconfirmed action. It goes back, it applies user A, applies user B, and now we have the final place where these two objects should have been. This is a really fun exercise or problem that we had to tackle. We got some inspiration. It's not 100% our awesome work that we've done because shooters have done this for a really long time. And in general, real-time games such as, I don't know, CSGO, Call of Duty, all of that, use a similar system in order to understand why exactly, as you move along on your screen, how come does the other user hit you and give you damage, right? Because you might not be, for the other user, at the same point where you're on your screen. But then, there, compared to us, where for us it's really simple, easy, because you can't really get wrong or you can't lose something in this whole equation, there you also get a prediction model. So as the user would move along and you would try to hit him, I would predict, using the speed, the velocity, and so on, where would the user be as my response or as my shot went through the server. So I know it takes me, with my ping that I have, around 200 milliseconds to go to the server and get some confirmation back. So on my machine, what's happening basically is I predict where that user would be 200 milliseconds from now. I go to the server. I ask the server, hey, I tried to shoot you there. Were you there? The server looks and says, oh, no. In the meantime, he pressed right. And he moved a little bit to the right, which means your shot just goes off. And at first, my system presumes, hey, you're winning this. But as it gets the answer from the server, you are actually, the server actually corrects you and puts you into place and said, no, you actually lost this one. You didn't touch him as you shot him, right? And that's the whole ecosystem, how the whole ecosystem works. And if you ever play one of those games and you actually shoot someone and it doesn't take any damage, or you're just frustrated like, man, I hit him, why the hell isn't he hit? Well, that's the reason why. The server is always right, and the other person's computer is always right about their movement, but you might be right about where you're pointing, and that's all. All right, this has been the exercise and overall the presentation. I hope you find some pieces of it useful. And if you have any questions, again, you can find me in the networking area and we can expand on any other subjects that you might want. I managed to stay in time, which is like it's a real win for me. But otherwise, this presentation was probably an hour and a half long because I still have slides afterwards, tackling different other problems that we encountered in the issue. You can find me on LinkedIn. You can just scan the QR code if you want to find me on LinkedIn and just shoot me questions about anything in the web ecosystem. And I'm not sure, Felipe, do we have any questions on F&T? So thank you, everybody.
Oh, perfect. We have nine minutes. It's okay for three questions. And the first questions is from Hanka. And will you choose the same tech stack today, or will you consider some different technologies?
That's a great question. So one thing to note is that as the ecosystem emerges and it changes a lot, we might have picked up different tech stacks. The reason why, for example, we went with Lit Element, it was, as we call it, it was the closest to the metal, so to say. It offered us as little influence from other companies or the ecosystem in what we were building. It's an open source project, and that's how we picked the technology in order to not be influenced by Facebook. If Facebook tomorrow wants to rewrite React and not sponsor it anymore, it's probably going to go downhill pretty fast. So you usually prefer to rely on open source or community-driven libraries and sponsor those communities with money in order to be able to continue their work, then actually pick one of the frameworks that are driven by one giant company. The agenda of that giant company is something that is very unpredictable in a corporate world. But to answer specifically the tech stack, I would consider a lot more Rust at this point because it's gotten way better at WASM builds. It's still, I think, 30 or 40% bundle overhead over the C++ version, but it's so much easier to just manage memory and manage objects and everything else. On the UI side, I would stick to Lit Element. I think in the past year or so, they just gotten so good at it that no other framework kind of makes sense to use at this point. If you're not looking to build something really, really fast, React, Vue.js, everything is just bringing overhead into your application. But one thing that I might be looking at, if you're not building an online editor, because this doesn't make sense to us, we're building an online editor, but if you're not building an online editor, Next.js is the shit right now. Like the ability to do server-side rendering and real-time rendering and everything as you want it configured brings so much power to the ecosystem. And if you're building a regular app, just go for Next.js. I think I should cover that.
Okay. The next question is from Christoph. How would you approach POC and new web application development for small teams with very limited resources? 2 or 3 peoples.
So what was the initial part? How would you see POC and new app development? This one?
Yeah.
Okay. Well, just my 2 cents, as I've been in the industry for quite a while, don't start anything without doing a POC. And more than that, as you're building that POC and you're using some technologies in order to build it, make sure you're reaching out to the people that are offering you those technologies. You would be surprised how open the guys from Lit Element or the guys from Mobex are to just jumping in and helping you out figure how to use their framework and make it something consistent into your application. But how would the POC work? Honestly, for the state management, it took us 1.5 weeks to create all of the 3 different applications and compare the results from it. So I think it's more than worth 1.5 weeks to make sure that you're picking the right technologies for what you're building your app. I hope that answers the question.
Okay, and the last question is how do you handle in multiplayer, especially when the multiple users are dragging at the same time after the second user releases and then reverts? Can you repeat it?
Yes. So just to make sure, basically, how do you handle undo in multiplayer, especially when multiple users are dragging at the same time, after the second user releases and then reverts? That's a great question.
Thank you.
No worries. That's a great question. Basically, what happens is comparing to the FRL updates that are going in multiplayer all the time, and basically you're pipelining all of the updates, the undo action is a very simple action. You are no longer in the second ecosystem where you're forwarding FRL updates. I don't forward, like if I had 1,000 different drag updates that I forwarded before in order to get from state A to state B, the undo action on all of that is actually just a persistent action. So it's very easy to do in the first scenario that we had, right? So we're no longer into the FRL update system. We're actually in a hybrid system where my changes, my undo changes, are simply decided by who reaches the server first. And then from there on, as multiple users are interacting with the objects, I am moving to this ephemeral system where I have state 0, where it's undoed from what the user did. And then I have 3 or 4 derived states for every single user that is dragging the objects on the screen. Does that make sense? Some people said yes. Hopefully it makes sense for everybody. If not, you can find me out there. I can deep dive into it, and we can look at exactly how this is happening behind the scenes. Is that all?
It's on. Thank you so much.
Thank you guys again. I hope you had a great time. Cheers.